Who solve systems of nonlinear equations in 5.4? All right, now, ladies and gentlemen, unlike linear systems of two equations and two unknowns, these systems could have more than one ordered pair solution. They could have like two ordered pair solutions or four ordered pair solutions or three ordered pair solutions, unlike linear systems, which could only have one unique ordered pair solution or none or infinite number. These nonlinear systems could have no solutions. They could have conceivably an infinite number of solutions, but they could also have maybe just one solution or two ordered pair solutions or three or four ordered pair solutions. Okay, it's possible with these systems, as we will find out. Okay, so we're going to just dive right in and we're going to just start solving some. Now, the first batch I'm going to solve by the substitution method. And that's a technique that we seen 2 days ago for solving linear systems. And here we go. The first equation is presented to us as y equals negative x squared plus 3. And the second equation is this linear equation, y minus 2x equals 0. So what we have here is we have a system of nonlinear equations in the sense that at least one of our equations is nonlinear. This equation here, ladies and gentlemen, is a nonlinear equation because x is raised to the second power. In fact, this happens to be what type of an equation? It's a quadratic equation. So we have a quadratic equation here. Quadratic equation. This happens to be a linear equation here, but the first one is nonlinear. So there we go, ladies and gentlemen. We're going to try to solve this system of two equations and two unknowns. And the substitution method is probably the nicest way to solve this system. Notice the first equation is solved for the variable y. And because of that, I can take this negative x squared plus 3, and I can bring that down and substitute it in for my, for my y variable into the second equation. So I'm going to substitute that expression, negative x squared plus 3, in for the y variable into the second equation. Upon making that substitution, my second equation is going to become negative x squared plus 3 minus 2x equals 0. And now we have to solve this quadratic equation for x. To solve this quadratic equation, I'm going to rearrange my terms to force this into descending order. I'm going to multiply through by a -1 to clear out that leading negative sign. And now this is our quadratic equation that we have to solve. Are we lucky enough to be able to solve it by factoring? Can I factor this trinomial here? Is this factorable?
Yes, isn't it -1 and 2?
Well,
no.
-1.
I got 3 and -1.
There you go, -1 and 3. You were close. So anyways, that left side of that quadratic equation factors. Being the case, we can now set our factors equal to 0 and then solve for x. Hence, we're going to get x is equal to +1 or x is equal to -3. All right, ladies and gentlemen, we still got to find the y coordinates of these ordered pair solutions, because if a system like this has a solution, of course, it has to be an ordered pair. And that ordered pair has to satisfy both equations simultaneously. So if x is equal to 1, to find y, I will use the first equation that's already solved for y, although you could use a second equation. I'm going to opt for the first equation. So y is equal to negative x squared. My x is 1, so the negative of 1 squared plus 3. So when x is equal to 1, y is going to be negative 1 plus 3, or y will be equal to 2. So y is going to be equal to 2. So one ordered pair solution that we've discovered is 1, 2. But there's another ordered pair solution. That occurs when x is equal to negative 3. So we take negative 3, substitute it into the first equation and for x, and then solve for y. So when x is equal to negative 3, y is equal to the negative of negative 3 squared plus 3. Y is going to be equal to negative 9 plus 3, which is negative 6. So y is equal to negative 6. Therefore, ladies and gentlemen, we have another ordered pair solution to this system. It happens to be the ordered pair negative 3, negative 6. Negative 3, negative 6. Does everybody understand how we got our two ordered pair solutions to this system, this nonlinear system of equations? 1, 2, and negative 3, negative 6. Any questions how we solve this nonlinear system by the substitution method? Now, we seen with the linear systems 2 days ago that if our system of two linear equations of two unknowns had a solution, it would be the point of intersection between the lines, correct? Geometrically speaking. Ladies and gentlemen, what's going on with this? How come we got two ordered pair solutions here? Can anybody explain to me why we have exactly two ordered pair solutions to this system?
The two parabolas intersect twice.
All right. This first equation is a quadratic equation, and it will generate a parabolic graph that opens downwards because we have a negative preceding the x squared term. Furthermore, its vertex point is going to be at 0, 3. So when we graph this first equation, it will be a parabola that opens downwards. The second equation is a linear equation. And if you put this in the slope-intercept form by adding 2x to both sides, you get y equals 2x. So this will be a line with a slope of 2 and a y-intercept of 0. Bottom line is, the reason why we got two ordered pair solutions, ladies and gentlemen, is because our line, the graph of our linear equation, is going to intersect, okay, the parabola, which is the graph of the first quadratic equation. You can see that that is entirely possible to get 2 points of intersection. And these would be the 2 points of intersection. That's why these are the two solutions of the system. Why don't we go to our graphing calculator and type these two equations in and convince ourselves that these would be the ordered pair solutions. Notice the first equation, you would want to solve for y. So y, the second equation would be y is equal to 2x. Let's go try this out on our graphing calculator. All right, I'm still waiting for my Commodore 64 computer to respond. I put in for a brand new computer to Santa Claus, ladies and gentlemen, so hold tight here. A faster computer. This is just a dual core computer, just has 2 CPUs. I'm going to try to go for a quad core. All right, here we go. We're going to try to graph these equations. So clear out any garbage, hit y equals. Let's type in that quadratic function, negative x squared. Oops. Negative x squared. Still wrong. Hold on. Negative x squared plus 3. Second equation, after we solve it for y, will be y is equal to 2x. So just type in 2x. All right, let's graph both these equations. And the first one will be a parabola opening downwards. There it is. And here comes the linear equation right there. Now we can't see it in its entirety because I need to zoom out. Go to my window setting, and I need to increase the minimum value on my x-axis. I'll go to -10 to +10 for a y, for an x max, space tick marks 1 unit apart, -10 to 10 by 1 on the y-axis. Now hit graph, and you'll be able to see there's your parabola. Vertex points at 0, 3, opening downwards. And here's your linear equations graph with a slope of 2 with the y-intercept at 0, the origin. Ladies and gentlemen, let's find these 2 points of intersection here. To do that, we go to calculate. Second trace takes us into calculate. Go down to the intersect function and grab it. Now to find the left point of intersection, I'm going to move my cursor in the vicinity of that point of intersection. Notice my blinking cursor is sitting on one of my graphs. I will designate the parabola as being the first curve. Hit enter. Your blinking cursor jumps to the other graph. We'll call this the second curve. Hit enter again. And there's that point of intersection, -3, -6. That's one solution we solved via substitution, -3, -6. To get this other point of intersection, we go back to calculate, second trace, go down to the intersect function and activate it. Move the blinking cursor in the vicinity of the other point of intersection over here. I will call the parabola my first curve, hit enter. Cursor jumps to the next graph. We'll call that the second curve, hit enter again. And there's your other point of intersection, 1, 2. That's our other solution to the system. Does everybody understand how we solve this system via graphing? Does this make sense, ladies and gentlemen, how we solve this using graphing? Any questions? I don't mind if you check your answers by using your graphing calculator. By all means, go ahead and do so. But like on a quiz or exam, if I want you to solve the system by substitution, I would like you to demonstrate the work here that I've demonstrated here, okay? So we just solved this system by substitution. And we discovered that, yeah, there are 2 points of intersection between the graphs. 1, 2 was down here. Well, -3, -6 was down here, and 1, 2 was up here. There you go. Any questions how we solve that system, both using substitution or graphing it on our calculator?
Can you just show me the calculator again, just real quick? Because I got the same lines and stuff. I just couldn't figure out how you got the points of intersection.
When you hit graph, do you see this?
Oh, yep, there you are.
All right, you see that now, right?
Yes.
All right, here we go. We got to go to calculate. Second button followed by your trace button gets you into calculate.
Okay.
Go down to intersect function, hit enter. Now, suppose you want to find the intersection point over here to the right. Notice you got to bring your cursor in the vicinity of the intersection point you want to find. Notice my cursor is sitting on the parabola. Yeah. Okay, just hit enter, and then your cursor will bounce to the other graph. Just hit enter again.
Oh, okay.
Hit enter again, and you get your point of intersection. You see that?
Yes.
To get your other point of intersection, you go back to calculate, go down and grab the intersect function again. But this time you have to move your blinking cursor in the vicinity of the left intersection point. Do you agree? Over here.
Oh, I get it now. Okay.
Hit enter, and you get it, correct?
Yes. Okay, that's why I was confused because I hit enter and I didn't realize we had to hit it that many times. Yeah. Okay, thank you.
3 times, yeah. Okay. Any other questions how we solve this system via calculator or the substitution method, ladies and gentlemen? All right. I'm not going to emphasize the graphing technique in all honesty with these nonlinear systems because, you know, graphing the equations is somewhat cumbersome or tedious. We really haven't studied conic sections yet. There's ellipses, hyperbolas, okay, circles. We haven't really touched base with those. So my interest is can we solve these nonlinear systems in a mathematical way, either by using the substitution or the elimination or the addition method, okay? All right. So let's put this one to rest. That one's done. Let's try another one. Solve by substitution. On any future quiz or exam, if I give you a system of equations to solve, and I want you to solve it a specific way to get full credit, please do demonstrate that technique. If you want to demonstrate some other method, I will, and get it correct, I will give you partial credit, but I will not give you full credit. If I just give you a system and say solve it, then you're free to solve it any way you want, okay? Let's see, solve it any way you want. So I would have to open up the possibility to you being able to use your graphing calculator too. So, and I would allow you to do that also. But I would like you to demonstrate the substitution method on this one. So that's what we will do. Here is an equation in our system, x squared plus y squared equals 25. And the second equation comes at us as 3y is equal to 4x. Ladies and gentlemen, this first equation is a nonlinear equation. Nonlinear, because our variables are not raised to the first power. Does anybody want to take a wild guess as to what type of graph this equation would generate? Just curious. Anybody want to take a wild guess? What kind of graph would we get if we graph this in the XY plane? Don't feel bad if you don't know it. I'm just throwing that out there. If anybody does know it, anybody know? Well, I'll just tell you, just for the record, ladies and gentlemen, it would be a circle. It is the graph of a circle where the center would be at the origin, 0, 0, and the radius of the circle would be the square root of 25 or 5. So it will be a circle. This is a linear equation, so its graph will just be a line. Ladies and gentlemen, conceivably, in how many maximum points could a line intersect a circle?
2.
2. Do you agree? So the maximum number of solutions we could get to this system is 2 solutions, 2 points of intersection. What's the minimum number of points that a line could intersect a circle? Minimum. Nowhere. Do you agree? A line may not even intersect a circle anywhere, in which case this would be the minimum number of solutions you could have, which could mean what? No solution. I got a question. Could we get one solution for this system? Is that possible? One solution?
No.
Is it possible to have a line touch a circle's graph at precisely 1 point? Actually, ladies and gentlemen, it is possible. We would have to say the line is tangent to the circle. And this point of intersection, which would be the only point of intersection, is called a point of tangency. There would be one solution in this situation. So when we get done solving this system, we either are going to get 2 solutions, no solutions, or 1 solution. Again, don't feel too bad if you did not know the graph of this is a circle. I'm just giving you a little extra for your money here, okay, and showing you geometrically what would really be going on with these equations here, okay? All right, let's go ahead and solve it. My biggest interest is, can we solve this by substitution, this system? All right, help me out here, ladies and gentlemen. How am I going to solve this system by substitution? Give me a jump start here. How do we solve by substitution?
Could you divide the bottom equation by 3 and then square the
what we're going to have to do, you are correct. We're going to have to take this linear equation and solve it for x or y. It does not matter which variable you choose to solve it for. Maybe we'll solve it for y. So let's do this. So solving for y by dividing both sides by 3. We're going to get y is equal to 4/3 x. Now we know y is 4/3 x. taking 4/3 x, substituting it in for the y variable into the first equation. We drop in 4/3 x right up here in for y. We then write our first equation having made that substitution. So therefore, we're going to have x squared plus 4/3 x squared is equal to 25. And now it comes down to, can we solve this quadratic equation in the variable x? So therefore, we have x squared. 4/3 x squared is going to be 16/9 x squared. Notice we have 1x squared. 1x squared plus 16/9 x squared. Another name for 1 is 9/9. So this is 9/9 x squared plus 16/9 x squared. And what's 9/9 plus 16/9? Gives you 25/9. So we got 25/9 x squared is equal to 25. Ladies and gentlemen, how do I get x squared by itself, as we will set this up for the square root method to solve this quadratic equation? How do I get x squared by itself?
Multiply by 9.
Okay, we can multiply both sides by 9. You know, we can even get there even quicker if we just multiply both sides by the reciprocal of 25/9. Just multiply both sides equation by 9/25. That'll be even quicker. Got to multiply the right side by 9/25. Notice the left side simplifies to just 1x squared. 1x squared. These are reciprocals. The product of reciprocals is 1. So therefore, we have 1x squared is equal to, now on the right side, these 25s cross cancel out, don't they? Leaving you with just 9. And now we take the square root of both sides to solve this quadratic equation for x. Don't forget to take the plus or minus square root of the number side. So therefore, the square root of x squared is x. X is equal to plus or minus 3. And so, ladies and gentlemen, it looks like we're going to have two. How many solutions are we going to have to this system? What do you think? Looks like what?
2.
Looks like 2 solutions because we got 2 values of x. So it looks like our line is going to intersect our circle in 2 unique points. That's what's going on here. All right, so to find the first solution, the ordered pair solution, we'll let x be 3. And then solving for y, we'll use the equation y is equal to 4/3 x. So therefore, y is equal to 4/3 times 3, which means y is going to be equal to 12/3 or 4. So one ordered pair solution is going to be 3, 4. To find the other ordered pair solution, x has to be equal to set equal to -3, in which case y is going to be equal to 4/3 times -3, which means y is going to be equal to -12/3, which reduces down to -4. So another ordered pair solution would be -3, -4. And you got your solutions to that system, that nonlinear system of 2 equations and 2 unknowns. Everybody understand how we solve that system using substitution? So yeah, geometrically speaking, if you're interested in knowing what's going on, yes, it looks like the graph of our second equation, our linear equation, will be a line. Looks like it would intersect this circle, the graph of the first equation, in 2 points. The 2 points of intersection would be 3, 4 and -3, -4. All right. That makes sense how we solve this system using the substitution method, ladies and gentlemen. Does anybody know how we would graph a circle on our calculator? How do you think we would graph that first equation on our calculator? Anybody have any ideas what we would have to do? Well,
Put the x squared on, subtract it from both sides?
yes, and then take the what of both sides? The
Square root?
Square root, yeah. So if you wanted to graph the circle on your calculator, it would be possible, but first you'd have to solve this first equation for y. And to solve it for y, you'd have to subtract x squared from both sides and then take the square root of both sides. Maybe I can demonstrate that because you never know, you might have to graph a circle in the future on your calculator. So why don't we just show ourselves how we would graph this equation on our calculator. We would first solve for y. subtracting x squared from both sides. And then we take the square root of both sides of our equation. Keep it in mind, it would be the plus or minus square root of the right side. Very important, don't forget the plus or minus. So y is equal to positive or negative the square root of 25 minus x squared. So here's what we're going to do. On our calculator, ladies and gentlemen, we're going to go to y equals, and we're going to let y1 be equal to the positive square root of 25 minus x squared. And y2 is going to be equal to the negative of the square root of 25 minus x squared. And then y3 will be our linear equation when we solved it for y, is going to be 4/3 times x. So let's go to our graphing calculator and let's type all these equations in and graph these two equations. All right. All right, so go to y equals, clear out all your fields. y1, I'm going to type in the square root. You got to hit the second and the x squared button. The square root of 25 minus x squared. Second function, I'm going to type in negative the square root of 25 minus x squared. Everybody see that there? Okay. And then for y3, I'm going to type in the linear equation, which was y was equal to 4/3 times x. Now when you hit graph, you should see the graph of a circle and a line. Ladies and gentlemen, the reason why this circle doesn't look like a circle, it looks more like an ellipse, okay, is because we don't have a 1-to-1 ratio with the number of pixels in the vertical versus the horizontal on this screen. We have more pixels in the horizontal direction on this screen than the vertical. It's not a 1-to-1 or ratio here. We can make our circle look more like a circle if you just go to zoom and you go down and select the z-square function. Zoom z-square squares up your screen, where there's a 1-to-1 ratio of the number of pixels vertically versus horizontally. When you do this, your circle will look more like a circle. Granted, we don't see the circle coming down here to hit the x-axis. Could we fix that? Well, maybe. Go to zoom, go down to z-decimal. Z-decimal. Well, I'm not sure what that did. For one thing, we can't even see the whole graph here. I would have to adjust my x-axis here, maybe go out a little bit further on my x-axis. All right, that's all jacked up. All right, so ladies and gentlemen, let's just go back to zoom and hit z-square. There we go, that's good enough. All right, now to find these points of intersection between the line and the circle, go to calculate. So second, trace, go down the intersect function. Notice my blinking cursor is up on the top circle, so we'll find this top intersection point here first. We have to hit enter to designate one of these graphs as being our first curve. Doesn't matter which one you call your first and second curve. Hit enter again, hit enter again. And guess what? It never worked. Error. Here's what we're gonna have to do, ladies. I'm gonna find these points of intersection here. You got to go back to y equals here. What we're gonna have to do is we're gonna have to turn off either the upper or the lower part of this circle temporarily. So I'm gonna go down here and turn the lower part of the circle off by going down to Y2, moving my cursor on the equal sign, then hitting the enter button. That'll toggle the graph from on to off. Now it's turned off. So when you graph this now, you only see the upper part of the circle graphed and the line. We turn the bottom part of the circle off. Now we can maybe find this point of intersection. Go to calculate, second trace. intersect. First curve is up here. Call it the circle, enter. Second curve is the line, enter, enter. There's your first point of intersection, 3, 4. And that was one of our solutions we found by substitution, 3, 4. To find that other point of intersection of the circle and the line down here in the third quadrant, we're going to have to go back to y equals and turn off the upper part of our circle graph. So moving your cursor for y1 on the equal sign, hit enter to toggle that graph off. Now we got to toggle the bottom part of our circle graph back on. Moving your cursor on y2 equals on the equal sign, hit enter, the bottom portion of the circle is turned on. Now hit graph. You'll see only the bottom of the circle graph, and here comes your line of intersection. Now we'll find this point of intersection down here. To do so, we go to calculate. Intersect. Notice my cursor is where it needs to be, down in this vicinity down here. I'll call the circle my first curve, enter. The line is my second curve, enter, enter again. There's your other point of intersection, -3, -4. There's your other solution. Any questions how we tackled this graphing via graphing, ladies? I'm just to kind of check her answer. Any questions how we graph that circle and that line? Then use the intersect function to find the points of intersection by systematically turning off one part of the circle's graph. Okay. All right, there we go. By the way, when you look at your examples in your textbook, which I strongly and sincerely hope you all are doing, they go over an example. They show you the keystroking on your calculator in one of those examples. So if you missed it there, you can get it out of your textbook, ladies and gentlemen. It's right there in the examples. Okay, let's move on. So that system had 2 solutions to it. Let's try to solve this one by substitution. Substitution. First equation is x squared plus y minus 3 squared equal to 4. And the second equation is y equal to -x minus 4. How would we solve this system by substitution? What would I do here? To solve by substitution, what am I going to do?
Put the y equals into the equation, the top one.
All right, so what am I going to substitute in for the y variable into the first equation? What's going in there?
Minus x minus 4.
That's right. The -x minus 4 is going to drop in here. So we're going to take this -x minus 4 and we're going to drop it right in place of the y in the first equation. Upon making that substitution, my first equation becomes you agree? Everybody understand the substitution we just made? Now we solve for x. -4 minus 3 is -7, so we can tidy this up and call it -x minus 7. And now, ladies and gentlemen, we have to solve this quadratic equation for x. We have no choice, but we're going to have to FOIL this out. What is -x minus 7 times itself? -x times -x plus x squared. -x times -7 is a -7x. -7 times a -x. Wait a minute here. What's -x times -7? Not negative. Yeah, it should be positive 7x. I apologize. What's -7 times -x? Plus another 7x. Finally, what's -7 times -7 as we multiply the last terms together? That's plus 49, and that's equal to 4. This is the quadratic equation we have to solve for x. 1x plus 1x is 2x, 1x squared plus 1x squared is 2x squared. 7x plus 7x is 14x plus the 49. equal to 4. To solve this quadratic equation for x, we have to zero the equation out. So we subtract 4 from both sides. In which case we get 2x squared plus 14x plus what? 45? And that's equal to 0. Can this be factored, this trinomial? Because if it cannot be, we're going to have to either complete the square on this or give it to the what? Quadratic formula to solve it. So how are we going to solve this? Can I factor this trinomial, ladies and gentlemen? Now, I don't care how you factor the trinomials, grouping method, trial and error method. The bottom line is we have got to get this trinomial factored. Anybody know how this thing would factor? Well, we're probably going to have the 2x and the 1x. We don't really have much choice for the first terms. We have a lot of choices for the second terms, though. What's going to drop in? 1 and 45, or 5 and 9, or 3 and 15, or 15 and 3, 9 and 5? What kind of combination here, ladies and gentlemen?
9 and 5.
What's that?
9 and 5.
9 and 5, you say? Okay. Well, let's see. Wait a minute here. 9 and 5, right? If I put the 5 here, I'll have 10x plus 9x is 19x, not 14x. If I put the 9 here and the 5 here and the 9 here, I'll have 18x plus 5x. That's not going to add up to 14x. I don't know. It doesn't look like 9 and 5 are going to work here. What else? So the plot thickens. How to factor this trinomial? Is it even factorable? Oh, it's factorable, I think. Let's see. 2 times 45 is 90. Are there 2 factors of 90 that add up to 14? Do they exist? Ten and 9? No. 2 and 45? No. 3 and 30? No. Oh, 4 and no, 4 don't go in there. 5 and what? 18? No, those don't add up to 14, do they? Are there factors of 90 that add up to 14? Double checking all the work here quickly. All right, well, that's what we got. That's the deck that's been dealt. So, can this even factor? Let's see, 3 and 30, 4 don't go in there, 5 does, 6. Does 6 go into 90? Yes, it does.
15 times, but
6 and 15, do you agree? Those just are not going to add up to 14, no. 7 don't go into 90, 8 don't, 9 does, 10 does. And that's about it, ladies and gentlemen. We're up a creek or a crick here. Do you agree? It doesn't look like this thing's factorable. No wonder we couldn't find it. Doesn't look like it's factorable. So, how are we going to solve this quadratic equation here? Might have to use the quadratic formula, correct? Unless you want to complete the square, which takes a long time. Maybe use the quadratic formula. All right, let's hit it with the quadratic formula. So x is equal to the opposite of b, which is the opposite of 14, plus or minus the square root of b squared, which is 14 squared, minus 4 times a being 2, times c, which is 45. Whoa. And that's divided by what? 2 times a. What's 2 times 2 times 2 is 4, correct? So I'm going to get negative 14 plus or minus. What's my discriminant? What does all this evaluate to underneath the square root? That's going to be 196 minus 8 times 45. What do we get? Whoa. about you, but I think we're getting what? A negative number, aren't we? Aren't we getting a negative 164 underneath the square root? No wonder we couldn't factor that trinomial. These are not even real, are they? These are imaginary. So ladies and gentlemen, we get negative 14 plus or minus I times the square root of 196 over 4. The bottom line is these are what? Non-real. And ladies and gentlemen, since our x coordinates of our ordered pair solutions are non-real, it does not appear that there will be any intersection points or any solutions to this system. Answer is no solution. The solution set is empty. Your author just puts an empty set. That means no solution to the system. There is no solution. Ladies and gentlemen, what do you think the graph of this equation is? Anybody want to take a wild guess? It will be a circle centered at 0, 3 with a radius of 2. This is going to be a circle centered at 0, 3 with a radius of 2. This, ladies and gentlemen, is a graph of a line where the y-intercept is -4 down here and the slope is -1. So the graph of this line is going to go something like this. Does it look like these graphs would intersect anywhere? Any points of intersection? None. And that's why this system has no solution, ladies and gentlemen. There would be no points of intersection between these graphs. That's why down here, when we tried to solve for x, we got something that's not real, a non-real solution. That means your system has no solution. Is everybody clear on that? No solution to this system. No solution. No ordered pair solutions. All right, that one's done. So far, we've been showing you how to solve systems using the what technique?
Substitution.
Substitution method, correct? All right, I'm going to have you guys solve one now by substitution. We'll call this classwork number 1. Ladies and gentlemen, what's today's date?
The 10th.
November 10th. This is the anniversary of the sinking of the Edmund Fitzgerald, an iron ore carrier up in Lake Superior on November 10th, 1975. All 29 crew members lost their lives. Anybody remember that episode? To tell you my age, ladies and gentlemen, I was 11 years old when that occurred. I remember that morning. The winds were howling that morning. I was getting ready to go to school, getting on the school bus. Winds were really howling. I guess the waves on Lake Superior that night when that iron ore carrier went down, the waves were as high as 25 to 30 foot waves on Lake Superior. And she sunk. She sits about 500 and some feet below the surface of Lake Superior, about 15 miles northwest of Whitefish Point.
Wasn't there a folk song that was written after that?
Yes, the folk song was written by Gordon Lightfoot, a Canadian songwriter. That is about that tragedy that occurred. That's correct. If you ever get a chance, look into it, research it. It's an interesting story, what happened that night. My uncle worked on the Mackinac Bridge at the toll booth that night. He said the winds were so strong, they had to shut down the Mackinac Bridge that night. Winds were too high. And that was the night she went down. All 29 crew members went to their death. No survivors, never found a survivor. They found a couple mangled metal lifeboats and some life rafts, life jackets, and that's all they found. All right, ladies and gentlemen, sorry, I just thought I'd throw that out there if you never even knew about the Edmund Fitzgerald. Is anybody old enough in this class to remember that or not? I'm just curious. Probably not, correct? All right, classwork 1, ladies and gentlemen, solved by substitution. You know, shipwrecks are no stranger to the Great Lakes. There have been many shipwrecks over the years on the Great Lakes. The Great Lakes can be very treacherous, especially in the month of November when you get strong pre-winter storms that come through. But the Edmund Fitzgerald is one of the most famous shipwrecks that have occurred on the Great Lakes. All right, there was a 729 long foot iron ore carrier, a freighter, and it went down. All right, ladies and gentlemen, let's see if you can solve this. this problem by substitution. Here it is. Y equals the square root of x. Second equation is x squared plus y squared equals 20. Ladies and gentlemen, I want you to try to solve that system by substitution. We'll come back and check your answer. Go ahead and try to do something with that. Did anybody at least get this far on the problem?
I did.
All right, good. Now we'll find our solutions. Remember, they got to be ordered pair solutions. Don't just get down here and call it quits, ladies and gentlemen. These must be ordered pair solutions. We got to find the y coordinates for these x coordinates. Uh-oh. What do you notice about this one? Is this a real or imaginary number?
Imaginary.
This is imaginary. And so, ladies and gentlemen, we can toss this out. This is not a solution to our system of equations here. The reason being is because it is not a point of intersection between the graphs, because you're not going to see the graph of an imaginary number in the real plane. Let's see if this generates a solution. Yeah, it looks like this one will. So what would be our only solution? Four, two? Did anybody get 4-2 as being the only solution?
I did.
Yes.
There you go. Yeah, we got to toss this one out because it is, I mean, it doesn't work as far as being a solution is concerned with being a point that's visible in the real plane. So like if you were to take the time and graph these equations here, Liz Almond, you would discover that this graph here only intersects this circle at one point, namely at 4-2. So if you were to, graph these equations, the graph of the square root of x is just going to be a graph that looks like this. That's the graph of the square root of x here. You see, that would be the graph of that. The graph of the circle is going to be a circle centered at the origin with the radius of the square root of 20, which is, let's say, a radius of 2 times the square root of 5. So you can see, Les, that this graph of the square root function would only intersect our circle in that one point. Do you agree? And that point of intersection would be 4-2. That makes sense there? Only one point of intersection, only one solution. All right. So that one is done, correct? All right, good deal on that one there. So that would be classwork number 1. We'll call that the first classwork there. All right, can we solve these systems by addition method? The answer is absolutely yes. And there's times when the addition method would be the way to go, as opposed to the substitution method, which would encumber more work. So let's solve by the addition. Oh, wait a minute. What's another name for the addition method?
Elimination.
Elimination. So ladies and gentlemen, please don't freak out if you see the word addition method as opposed to the elimination method. They mean the same procedure, okay? All right, here we go. Here's our first equation. 3x squared plus y squared is equal to 21. This is going to be the graph of an ellipse. This is not the graph of a circle. It's the graph of what's called an ellipse, which is a degenerate circle. This ellipse in general would look like this. The major axis would be vertical, or the minor axis would be horizontal. Again, you're not responsible for knowing the graphs of these equations. I'm just kind of giving you a little extra for your money here, okay? We haven't formally studied conic sections yet, all right? So I'm just interested, can you really solve these systems using substitution or elimination, all right? Don't worry about the graphing aspect. I'm just kind of giving you a little bit more robust understanding as to why we're getting the solutions we're getting by showing you the graphical interpretation. All right, the second equation would come at us in the form of 4x squared minus 2y squared is equal to negative 2. Ladies and gentlemen, the graph of this would be a hyperbola. This is called the graph of a hyperbola. And its graph will look like this, where you have a branch that opens upwards and you have like a parabolic branch that opens downwards. This is called the graph of a hyperbola. You can see that the maximum number of points of intersection between our hyperbolic graph, which is this, versus the graph of the ellipse, could afford us a maximum of 4 solutions. Do you agree? There could be a maximum of 4 intersection points between these graphs here. All right, let's try to solve this via elimination. What variable do you want to eliminate, x or y? Which one would be the easier variable to eliminate? X or y?
Y.
Y. Let's try to make this become a positive 2y since we have a negative 2y squared here. To accomplish that, I would multiply my first equation by 2. So let's multiply my first equation by 2. Therefore, my equivalent first equation will be what? 6x squared plus 2y squared Don't forget to multiply the 2 by the right-hand side, 21. That'll give you 42. Sliding the second equation underneath this equation, notice our y variable will now be eliminated upon adding these equations together. So adding these equations up, we get 10x squared. Y is gone, eliminated. The right-hand side is 40. Ladies and gentlemen, we can now solve for x. To solve for x, we isolate the x squared variable on the left side of our equation by dividing both sides by 10. Hence, this implies that x squared is going to be equal to 4. Now we take the what? Take the square root of both sides of our equation. Don't forget to take the plus or minus square root of the number side, in which case we have x is equal to positive or negative 2. Positive or negative 2 for x. All right. We still got to find the y coordinates. We're not done here. So if x is equal to positive 2, what equation do you want to use to find the y variable? You can take your pick. You can choose this equation or this equation or this equation. Ladies and gentlemen, which one you want to use? It doesn't matter. Just pick one.
The 4x squared.
All right, this one. You want to use this one?
Yeah.
All right. So we can use that one. So using our choices to choose this 4x squared minus 2y squared minus equals negative 2. In for x goes 2, 2 gets substituted in for x, in which case we have 4 times 2 squared minus 2y squared is equal to negative 2. Now we have to solve this quadratic equation for y. This is going to be 4 times 4, which is 16. Subtract 16 from both sides of our equation, and we therefore have 16's drop on the left, negative 2y squared equal to negative 18 on the right. Divide both sides by negative 2 to isolate y squared, and therefore we get y squared is equal to 9. Now, ladies and gentlemen, take the square root of both sides of this equation to solve for y. Don't forget to take the plus or minus square root of the right side, the number side. So y would be equal to plus or minus what? 3. All right, so look at, we have found 2 of our solutions. When x is equal to 2, we discovered that y is equal to plus or minus 3. So ladies and gentlemen, we could have 2 solutions, positive 2, positive 3, or positive 2, negative 3. Again, when x is equal to 2, we discovered y is equal to plus or minus 3. Hence, we have 2 solutions. Are we done? Are we done?
No.
No, because I just look at, because remember, back up here, can't forget, x could be equal to positive or negative 2. I just found what y would be if x is positive 2. Y would be plus or minus 3. We got to now let x be equal to negative 2. So we're still not done. Now we got to let x take on the value of negative 2 and solve for the y coordinates. Try not to forget to find all your ordered pair solutions. Now, if x is negative 2, to find y, again, you can make use of any equation. I guess we'll use this one again. So we have 4 times negative 2 squared minus 2y squared equals negative 2. Again, this is going to be 16. And hey, do you agree that we're going to get the same solutions for this equation that we did for this one here? They're identical equations. So why go through the same song and dance? Ladies and gentlemen, we're going to get plus or minus 3 again for y. Hence, what's our other 2 ordered pair solutions? X could be negative 2 and y could be positive 3, or x could be negative 2 and y could be negative 3. We are done. We have found our 4 points or 4 ordered pair solutions to this non-linear system of 2 equations and 2 unknowns. You can see that, yes, it would appear that the ellipse, the graph of the first equation, would intersect the hyperbola, the graph of the second equation, in 4 unique points in the plane. And that's why we got 4 ordered pair solutions. So these 4 ordered pairs satisfy both equations simultaneously. Any questions how we solve that system by using the addition or the elimination method, ladies and gentlemen? That's a classic problem there. It's an excellent example illustrating this addition or elimination method for nonlinear systems. We understand how we got all our solutions down here, letting x be 2 first, finding y, and then letting x be -2 to find y. Okay, don't forget to find all of your solutions. It's easy to get things, lose things in the shuffle down here because a lot's going on down here, okay? But you got to understand, x could be positive or -2. In which case for both cases, we spawn 2 different values for y, positive or -3, or positive -3, okay? All right, that's called the addition method. That's called the addition method, ladies and gentlemen. I would like you to try this problem using the addition method. Do you guys think you're up for the task? Classwork number 2. Addition method. The addition method works essentially the same way as it did for systems of 2 linear equations of 2 unknowns 2 days ago. It's just that now we got nonlinear equations, but we can still use the addition method on them. Okay. All right, let's see if maybe you could try this one here. We'll call this classwork 2 for the 10th day of November. All right. Now, the first equation comes at us in the form of x squared equals 1 minus y squared. Second equation is 9x squared minus 4y squared equals 36. If I want you to solve by elimination, what is the first thing we need to do, ladies and gentlemen? What's the first thing we need to do before we apply the elimination or the addition method? What do we
Move the negative y squared to the left side of the equation.
We got to get this equation in the form where x and y are on the same side of the equation so we can line up our like terms in columns. So we got to solve, bring this negative y squared over to the left side to join the x squared. To do that, we add y squared to both sides. So therefore, x squared plus y squared is equal to 1. When I add y squared to the right, the y squareds will drop out to 0. So all I did here is add y squared to the right and the left side of this equation to get my first equation in this equivalent form. Now we slide the second equation underneath here. And now, ladies and gentlemen, I want you to take this problem the rest of the way by employing the elimination method. See if you can take care of that now. Classwork 2. Well, how are we doing out there? How's it going on this problem?
I got the X value, but I'm kind of stuck. Or
All right, what variable do you choose
just-
to try to eliminate? Which variable?
I tried to eliminate Y.
Okay, to get rid of Y, we would multiply this first equation by 4. So when we do that, our new equivalent first equation is going to be 4x squared plus 4y squared equal to 4. Second equation, I'll slide underneath this equation unaltered. Now we add these equations together. Notice the y's are eliminated. The x's add up to 13. The x squareds add up to 13, x squared. And on the right side, we got 40. Now, what we have to do is try to solve for x. Doesn't look too nice here. We divide both sides by 13. And we get ourselves a real messy situation. Over here on the right side, 40 13s is not a perfect square by any stretch of the imagination. But anyways, if you solve for x, you'll get plus or minus the square root of 40 over 13, which I'm just going to leave it like this for now. I'm not going to simplify this yet. To try to find y, we would choose one of our equations up here and then substitute in, you know, plus square root of 40 over 13 or negative. Like if I go with the first equation here, I got a question for you. If I go with the first equation, does it matter whether I substitute in the positive or the negative version of the square root of 40 over 13? Do you think that's going to matter?
No.
No, because we're squaring it anyways. It don't matter if you put the minus version in or the plus version in here. You square it, it's going to come out positive anyways. So whatever. Let's use the first equation here. X squared plus y squared equals 1. In for x, I'm going to substitute in. It don't matter. I mean, it don't matter if you put the plus or the minus in here because you're going to be squaring it anyways. And when you square it, it's going to walk out as a positive anyway. So now we'll attempt to solve for y here. When you square this square root, what drops out of it is just going to be 40 over 13 plus y squared is equal to 1. And ladies and what we're going to do now is solve for y squared by subtracting 40 13ths from both sides of our equation. So we subtract it from the left, of course, it drops out. To the right, we're going to have 1 minus 40 over 13. Common denominator of 1 and 13 is 13. Another name for 1 is 13 13ths. 13 13ths minus 40 13ths is going to net us what? What's 13 minus 40? Negative 27, I believe. Oh, here's the problem. When you take the square root of both sides, ladies and gentlemen, you're going to get y is equal to the plus or minus square root of negative 27 13ths, which means these are not real, are they? They're imaginary. So what do we conclude, ladies and gentlemen, about the solutions to such a system as this?
There are no solutions.
There would be no solution to this system. You are correct. Ladies and gentlemen, the system has no solution, and we're done. That's it. No solution. We did everything legal, and yet we come down to a situation where y turns out to be imaginary. So you cannot have imaginary y coordinates of ordered pair solutions because they would not appear anywhere in the real plane. You can't graph imaginary numbers in the real plane. They don't even, they have no place in the real plane. All right, so there'd be no solution. Did anybody ascertain that or just curious? Anybody? Anybody out there?
I got the X values and I ended up thinking that the ultimately there was no solution,
Yeah.
but I did not get what was underneath the root.
Oh, but when you got your X values and you tried to find your Y values, did you get Y values that were like non-real at all or what?
Yes, I got I think I miscalculated the subtracting the fractions, but besides that, everything.
Yeah, don't worry too much about the fractions being miscalculated. Bottom line is if you get I, do you agree, for X or for Y, we slam on the brakes and we got to toss those out, correct? They cannot be solutions. Does that make sense there? All right, so there would be no solutions to this, this system here. All right, so that illustrates the use of the addition method there, ladies and gentlemen. And okay, that's the addition method. We'll go with that. Now, I'm going to show you that. I want to show you this next system. I want to show you what you can do from time to time, and this is something that you do quite a bit in calculus, is employ what's called a U substitution. They're used all the time to help you see the forest for the trees in the simplified situations, so that the situation becomes more tractable, more manageable as far as the solution is concerned. So what we're going to do is we're going to try to do this right here. We're going to try to solve this system here. Now notice I did not specify a particular technique to attack this system with. I will specify that in a moment. There's our first equation, yuck, right? And here comes the second equation. Like that there, okay? All right. Now, this is a rather messy, system here because, we got fractions everywhere, and even more troubling is the fact that we have variables appearing in our denominators of our fractions. Notice it kind of looks like if we added these equations together, these terms would drop out, which is nice. But I'm going to show you an even nicer way to tackle this system here. It's by making use of what is called a U substitution here. I'm just going to display this method to you because some of you may remember this technique and may employ it in the future on similar situations, or this may actually help you to understand U substitutions better when you get into your calculus. A U substitution. Suppose that I decide to let the variable u be equal to 1 over x squared. And suppose that I let another variable v be equal to 1 over y squared. Perfectly harmless thing to do. You can always do, employ a substitution. Now, by going with these substitutions of the variable u being this, v being this, how would that help me to simplify my system of equations here, which is highly nonlinear to say the least? Well, in place of -3 over x squared, what can I substitute? Well, let me rewrite -3 over x squared so it's easier for you to see what's going on. Do you agree I can rewrite -3 over x squared as -3 times 1 over x squared? It's the same thing as that. Do we buy that? And 5 over x squared, do you agree, is the same thing as if I say 5 times 1 over x squared? Same thing. All right. But ladies and gentlemen, what am I going to substitute in place of 1 over x squareds here? What's going in for 1 over x squareds?
U.
I let u be that. So look at this. I'm saying let u be 1 over x squared, so I can put a u in here and substitute a u in here. And when we do that, our equations are going to look a heck of a lot nicer. My first equation is now going to look like 3 times u. 3 times u. And what drops in for 1 over y squareds here? V drops in here, and v drops in here. So upon making these substitutions for 1 over x squared and 1 over y squared, this first equation becomes -3u plus v equals 13. Second equation becomes 5u minus v equals -5. Wow. Look at how nice this system looks here. Do you agree? Compared to this mess we had here. See how nice U substitutions can make your systems or situations look? The point of a U substitution is to take a real complicated looking situation and to try to simplify it so that we can better understand what needs to be done. That's the purpose of a U substitution. And you use U substitutions all the time in higher level math. Calculus, differential equations make use of a lot of U substitutions. All higher level math make use of U substitutions to help us cut through the chase, to help us see the forest for the nitty gritty trees, okay? All right, now, ladies and gentlemen, it's easier to see what we need to do. How do we solve this system? We just use the addition or the elimination method. Add these equations together. Negative 3u plus 5u is 2u. The v's drop out. Then we're left with what? 8. Now we can solve for u. Divide both sides by 2, and we get u is equal to 4. To solve for v is equally simple. We know u is 4. We can grab one of our equations. I'll maybe grab this first one here. In goes 4 in place of u. And now we can solve for v. So we have negative 12 plus v is equal to 13. Add 12 to both sides. And therefore it appears that v is going to be equal to 25. But we're not done. Remember, we were not being asked to solve for u and v. We were being asked to solve originally for what? For x and y. So what we have to do now is we have to back substitute. In for u, we bring back 1 over x squared. In for v, we bring back 1 over y squared. So therefore, upon back substituting, since u is equal to 4, 1 over x squared is equal to 4. Instead of saying v is equal to 25, which it is, we now bring back what v was set equal to, namely 1 over y squared is equal to 25. And now you got to admit, we have much simpler equations to solve now for x and y. To solve this equation, I will reciprocate both sides of this equation, flip both sides upside down, in which case I got x squared is equal to 1 over 4. Take the square root of both sides of my equation, and ladies and gentlemen, I get x is equal to plus or minus the square root of 1/4. But what's the square root of 1/4? 1/2. Flipping both sides of this equation upside down, we get y squared equals 25. Take the square root of both sides. Y is equal to plus or minus square root of 25. Y is equal to plus or minus 5. So I have a question for you. How many different solutions are we going to have to this system? How many different solutions are we going to have, ladies and gentlemen? How many different solutions are we going to have to this system?
4.
We will have 4. You are correct. Because x could take on any one of these two values. Y could take on any one of these two values. So you know what your solutions are going to be? You could have a positive 1/2 and a positive 5, or you could have a positive 1/2 and a negative 5, or you could have a negative 1/2 for x and a positive 5 for y, or you could have a negative 1/2 for x and a negative 5 for y. 4 different solutions, and there you go. 4 different solutions.
Okay, so question.
Yes.
When we were trying to find where what the y value is, how come you didn't flip the like the 25?
Yeah, it should be flipped. Son of a gun. I forgot to flip 25 over 1. It should be 1 over 25. So the square root of 1 over 25 is what? Plus or minus 1/5. My bad. So the y coordinate should be positive or negative 1/5, ladies and gentlemen. Thank you for that. Unbelievable. You know, I never used to make little mistakes like this. I mean, I hope this isn't a precursor of things to come in my life, because if it is, I got to think about moving on pretty soon here. If it gets any worse. This should be 1/5 or negative 1/5. 1/5 or negative 1/5. You are correct. Yeah, those would be your 4 solutions. Sorry about that. All right, ladies and gentlemen, that makes sense there. you got to admit, these U substitutions, this U and V substitution really did take a messy system. Do you agree? And really cleaned it up for us, didn't it? Made it so much nicer looking, so much more streamlined looking. That's the purpose of these U substitutions. And like I said, some of you are going to be going on into calculus, and you'll be using U substitutions quite a bit. They help you to simplify complicated situations. They help you to see, like I said, the forest for the trees. I would like to do a couple of application problems with nonlinear systems, ladies and gentlemen, before we call it quits here today. So I would like to go to the textbook. Let me guess. I bet I have to sign in again because I'm sure this application timed me out. So please bear with me. Let's see, or maybe, wow, huh. This is interesting. Maybe I did not get timed out, or. Well, come on, in this lifetime. Let's try this again here. Probably timed me out. All right. I'm going to go to page, let's see, page 40, page 533. Page 533 in our textbook. All right, so we're going to go to page 533 in the textbook. And I would like to look at just a couple here. Problem number 47 here, ladies and gentlemen. It says the floor of a rectangular bedroom requires 240 square feet of carpeting. Molding is placed around the base of the floor, except at 2 3-foot doorways. If 58 feet of molding is required around the base of the floor, determine the dimensions of the floor. They want to know how many feet long this floor is by how many feet wide it is. All right, so we're going to try to attack this problem here. So we have a rectangular floor plan for this room in our house. And we do have some doors here that open up to this room. So I got to allow for the doorways. Okay, I'm drawing a picture right now, just bear with me. Okay, so we have a door here and we have a door down here. And this is 3 feet. And this is 3 feet. Okay. Now they tell us the area of this floor is to be what, 240 square feet. And they tell us that we have 58 feet of molding. Let's see. All right, so we need 58 feet of molding to put around the base or the perimeter of this rectangular room here. So ladies and gentlemen, how are we going to get the dimensions of this room? I'll tell you what, let's call the length X. Suppose the length of this room is X feet. The width we'll designate as being Y feet. So let X be the length, let Y be the width. They want us to find X and Y, the dimensions of this room. All right. Now, as far as the 240 square feet, this constitutes what? Perimeter or area? What is this figure here? Perimeter or area? Area. How do you find the area of a rectangle?
Multiply the length and the width.
Length times width. So the area is going to be X times Y. But ladies and gentlemen, they tell us the area is 240 square feet. So we have one equation in our system. X times Y is equal to 240. That's one equation that we have. It's called the area equation. The other equation is going to be the perimeter equation involving the molding. They say that we had to use 58 feet of molding. Hey, would I use molding on the doorways here? Would I put molding across the doorways, the bottom of the doorways? They're going to be molding here, ladies and gentlemen? No, you don't attach molding to the floor of a doorway. There's no molding here. There's no molding here. So, ladies and gentlemen, we have to come up with a molding equation. We have the area equation. Now we have to deal with the molding equation. We used 58 feet of molding to go around the perimeter of this room. So what's that?
Would that molding equation be x minus 3 squared plus y squared equals 58? Okay,
you're on the right track. It wouldn't be squared though, but do you agree? How much molding, ladies and gentlemen, would be needed for here to here? Well, here to here is x feet, but we don't need 3 feet of molding. Do you agree? Because we got a doorway here. So you are correct. The amount of molding we're going to need for the length here is going to be x minus the 3 feet. But we also need that amount of molding here too. X minus the 3 feet. We don't have to use 3 feet of it because we have doorways here. So x minus 3 feet. So we wouldn't say x minus 3 squared. We would say x minus 3 plus what?
X minus 3.
That's right. X minus 3 plus x minus 3 of molding. We're talking perimeter here. And we also need y feet of molding here and y feet of molding here. Plus y plus y. When you add up all these linear lengths of molding, it better be equal to 58 feet. Ladies and gentlemen, we now have another equation in our system. So now we have developed a system of two equations and two unknowns. I was about to say linear equations. This is not a linear equation. This one is, but this is not a linear equation. So this is a nonlinear system. All right, so the second equation, upon cleaning it up, we got x plus x is 2x. Negative 3 minus 3 is minus 6. Y plus y is plus 2y. And we got 58. Further cleaning up of this second equation by adding 6 to both sides to get this equation maybe in standard form, we would have 2x plus 2y is equal to 64. So now, ladies and gentlemen, we have a system of two equations and two unknowns. How would I solve this system? Would you use addition method or elimination method? I'm sorry. Would you use the elimination method or the substitution method? What do you think? This sure doesn't look like it's ready or what, conducive for the addition or elimination method. Do you agree? No, it's not built for that. We should use the what method?
Substitution.
Using substitution. Yeah, substitution is the way to go here. So using the substitution method to solve this system, I have to solve this equation for x or y in terms of the other variable. Doesn't matter which one. I will solve for y. Therefore, y is equal to 240 divided by x. I divide both sides of this equation by x to solve for y. Now, ladies and gentlemen, we know y is 240 over x. Knowing that, I can replace in my second equation 240 over x and for the y variable. That'll drop in here for y. Therefore, my second equation upon making that substitution is going to be 2x plus 2 times y. But what's dropping in for y? 240 over x. And that's equal to 64. Now we have to solve this nonlinear equation for x. So we have 2x plus 2 times 240 is 480 over x equals 64. I'm going to get rid of this fraction by multiplying both sides of my equation by x. Don't forget to multiply the right side by x. So we got 2x squared plus these x's drop out, cross cancel out, leaving you with plus 480 equal to 64x. Zeroing this equation out by subtracting 64 from both sides, 64x from both sides. Can we, ladies and gentlemen, factor this left side to solve this quadratic equation for x? You know, it'd be a lot easier if we factor 2 out of all the 3 terms first. It'll make our life a million times easier in factoring this trinomial. Can you think of 2 factors of 240 that add up to negative 32? Well, you got a calculator out there, ladies and gentlemen. Can you find 2 factors of 240 that sum up to negative 32? 2 and 120 don't work. 3 and 80 don't work. 4 and 60 don't work.
Negative 12 and negative 20.
Thank you. So therefore, this trinomial factors in x minus 12 times x minus 20. That will definitely work. That's what the doctor called for. Now, ladies and gentlemen, we set these factors equal to 0 and solve for x. Solving for x, we get x is equal to 12, or x is equal to what, 20? So we get x is equal to 12 feet, or x is equal to 20 feet. Now, if x is 12 feet, what would y have to be? Well, let's use this equation right back up here to find what y would be. So if x is 12 feet, y is going to be 240 divided by 12. So y is going to be 240 divided by 12, which means what, 20 feet? Or later on, if x is equal to 20 feet, y would be equal to 240 divided by 20, which is to say what? 12 feet. Huh. So what do you think the dimensions of the room are? Either if you view it from these or these, it don't matter. These are saying the same thing, are they not? Ladies and gentlemen, the dimensions of the room would be what?
20 feet by 12 feet.
Yeah, it would be 20 feet. 20 feet by what? 12 feet. 20 foot by 12 foot room. There you go. You got your dimensions of your room. You solve for x and y. 20 foot by 12 foot dimension room. Questions how we attack that word problem there? Questions how we attack that word problem? That was number 47. Application problem in section 5.4. The application problem 5.4. Good. Done with that problem. Let's look at one more. Number 49. A rental truck has a cargo capacity of 288 cubic feet. That's volume. A 10-foot pipe just fits resting diagonally on the floor of the truck. If the cargo space is 6 feet high, what's the dimensions of the truck? What's the length, width, and height? Well, we already know one dimension. What dimension do we know automatically?
The height.
We know the height. It's 6 feet high. We got to know what the length and width of that that payload is on that truck. So to do this problem here, number 49, section 5.4, ladies and gentlemen, I think we need to look at the top view. If we were to get up on top and take the top lid off this truck, or the top of the truck off, and look straight down on that truck, straight down from above on that truck, we would see, do you agree, we would see this? You agree this would be the top view? And we got a pipe here lying diagonally that just fits in the truck. And this pipe is 10 feet in length. Ladies and gentlemen, all we got to do is find the dimensions of this part of the truck. We'll call this X feet. We'll call this Y feet. We know the truck is 6 feet tall. So coming out of your paper would be 6 feet tall, a wall that's 6 feet tall in this truck. You got to use a little imagination if you want to view this in 3D. So in other words, 3D here, 3D would have us viewing this truck like this, where we would have a wall that comes up 6 feet tall. You see that, ladies and gentlemen? You have to use a little imagination here. Okay. Real imagination. We're trying to find what? This dimension of our truck bed, y by x. We already know the height is 6 feet. They already tell us that, correct? All right. I have a question for you. How can we find x and y? Ladies and gentlemen, we're going to have to set up a system of equations to help us here. They tell us the volume of this truck is what? What was the volume of that truck's shell? Interior was 288 cubic feet. We know the volume is 288 cubic feet. That's the volume. That's the amount of like sand you could put in the truck if you pack it full of sand, or water if it could hold water. 288 cubic feet. Ladies and gentlemen, how do you find the volume of a box? Because that's really what we have here is a rectangular box. How do you find the volume of any box?
Length times width times height.
Yeah, so we'll take x times y times the height of the box, which is 6 feet. So x times y times 6, I'm going to call that 6xy. Hence, we have one equation in our system we just developed. 6xy is equal to 288. Height times length times width, or height times width times length, gives you the volume of that truck. Now, we need another equation, and the other equation is going to come from this diagram. If we look straight down from above and take off the top of this truck, we're looking at this floor plan of the truck. Ladies and gentlemen, I have a question for you. What equation will relate x and y in this diagram? Anybody? What can we do here? I'm going to give you a hint. What kind of an angle is this?
Would it be x squared plus y squared equals c squared, or
10 squared. You're
yeah,
correct.
10 squared.
Ladies and gentlemen, do you see that we have a right triangle here? Because the pipe lies diagonally on the floor of the truck and just fits. We have a right triangle. So therefore we can use what's called the what? The Pythagorean what? Theorem? That was developed by a fellow by the name of Pythagoras thousands of years ago. Pythagoras discovered that if you take the longest side of a right triangle, called the hypotenuse, which is always the side opposite the 90-degree angle, if you square its length, it will be equal to the sum of the squares of the two shorter sides of the right triangle. That's always true for a right triangle. That's what Pythagoras discovered thousands of years ago. This theorem's been around for a long time. So, ladies and gentlemen, we have another equation in our system. The fact that x squared plus y squared is equal to 10 squared, which is what, 100. Now, how would we solve this system? What would be the most efficient way to solve this system? Elimination or substitution? How are we going to solve this system?
With substitution.
Substitution, yes. We could maybe solve this first equation for maybe y or x. I'll solve for y by dividing both sides by 6x. So there you go. Hey, does 6 divide into 288 evenly? Can we reduce this?
Yes, it divides into 48.
48, so we got 48 over x. So, ladies and gentlemen, we now know that y is equal to what? 48 over x. Even nicer. Now we use substitution. In for the y variable into the first equation, I will substitute 48 over x. So 48 over x is going to come up here and drop right in for the y variable. Hence, upon doing that, my first equation collapses down to x squared plus 48 over x squared equals 100. And now we just have to solve this quadratic equation for the variable x. We have x squared. What's 48 times 48? I do not have that one in my back pocket. What's 48 squared?
About 2,304.
What is it, 2,304?
Yes.
2,304 over what? X squared is equal to 100. Let's get rid of this fraction by multiplying both sides of my equation by x squared. Hence, when we multiply both sides of our equation by x squared, this becomes x to the 4th. Oh no, x to the 4th power. Are you kidding me? Well, that's the deck that's been dealt. So we got x to the 4th. And when you multiply x squared by this fraction, the x squareds cancel out, leaving you with 2304. Multiplying the right side of this equation by x squared, you get 100x squared. We have to solve this 4th degree polynomial equation for x. How are we going to do that? How are we going to solve for x? Let's zero this equation out. We'll zero it out by subtracting 100x squared from both sides. Oh boy. Can we factor this? Ladies and gentlemen, do there exist two factors of 2,304 that sum up to negative 100? Anybody out there quick with the calculator? You know, you could use the quadratic formula also to solve this, but I'm just curious. Can anybody get on your calculator? Let's have a race. Who can find me two factors of 2304 that sum up to negative 100? Go ahead. See, can you find something? Use that calculator, ladies and gentlemen. Put that calculator to work. Let's see here. Two factors of 2304 that up to 100. Not an easy task. Not an easy task. Or we could just use the quadratic formula. I don't know, but
negative 36 and negative 64.
Wow, is that right? So therefore, this factors into x squared minus 36 times x squared minus 64. You know, this sure sounds possible. Setting both these factors equal to 0 and then solving for x. So we have x squared minus 36 equals 0. That means x squared is equal to 36. Or setting x squared minus 64 equal to 0, solving for x, we get x squared is equal to 64. Taking the square root of both sides of these equations, that would imply that x is equal to plus or minus 6. Taking the square root of both sides of this equation implies that x is equal to plus or minus 8. Which ones do we toss out? Which ones make no sense in the context of this problem?
Negative 6 and negative 8.
Yeah, throw out the negatives for x. There's no such thing as a negative length, okay? So we're going to toss out the negatives. We're going to say x is equal to 6 feet or x is equal to 8 feet. Now, ladies and gentlemen, we still got to solve for y. But look at, if x is 6 feet, y would be 48 divided by 6. What's 48 divided by 6?
8.
8 feet. Or if x is 8 feet, y would be 48 divided by 8, which means y would be what? 6 feet. Bottom line, ladies and gentlemen, what's the dimensions of this truck? We know it's got to be a what? 6 foot tall by 6 foot by 8 foot truck. Do you agree? So the dimensions of this truck are going to be 6 feet high by 6 feet wide or length or whatever you want to call that by 8 feet. It doesn't matter which one you call the length and the width here. The bottom line is these are the dimensions of our truck. 6 feet high by 6 feet by 8 feet. 6 feet by 8 feet by 6 feet high. You got the dimensions of your truck. And we're done with that problem. Okay. Everybody see how we solve this nonlinear system of equations to solve these word problems here? Nice job on that factoring. Wow. You know, I don't think I could have got that as quick as you did. That's amazing. Congratulations on that one. Kudos there. Okay. All right, ladies and gentlemen, that makes sense here? Solving a couple of word problems by using nonlinear systems of equations there. All right, great. Well, that's it for tonight, ladies and gentlemen. I have exhausted my time, so you can just, give me those two classworks there. And I will update Alex for problems on 5-4. And with that, I will let you go. You guys have a great, safe weekend, okay? And batten down the hatches. I guess we are going to get some wind out of this next low that's coming through here. Maybe not as strong as November 10th, 1975, but nonetheless, some strong winds of this next low pressure system when it winds up in the Great Lakes here. So hang on tight. If you go out on the seas, you know, I wouldn't go out. I would not go out on the Great Lakes this weekend. The winds are going to be too strong. So I would just stay in harbor. All right, ladies and gentlemen, you have a great night. I'll stay on the line if you have any other questions or concerns.